looks like we can get started as people are joining. So today will be our 11th meeting of our SIGCOMM Paper Reading Group. So yeah, time really flies. I mean, yeah, I think we started in October and now we are hitting double digits of our meetings. So 11, right? So I and also we applied for a non-paper session at this year's SIGCOMM discuss how we can do better to serve the community with this reading group. So we already submit our proposal. So fingers crossed to see. Hopefully it can get approved. But okay, let's go back to our meeting. So today we are going to read a paper from SIGCOMM 2024.
这个看着你封面就是死人家都，我感觉
R-Pingmesh, a service-aware RoCE network
死定改
monitoring
回来
and
了。
diagnostic system.
你是发炎吧？
Only by looking
不
at
不
the
不，不会是这样的，这样吧？
title that hey, this is the network monitor and diagnosis system, right? So because we have learned a lot about the machine,
这段别
especially design and scheduling of data center networks, and in particular large language model or AI training and serving systems, right? I think we have read Crooks and also maybe HPN, also Kefei cache and etc. We have read several papers regarding machine learning system, but all machine learning system essentially works essentially now resides in RoCE networks, right? So so this week we will focus on focus on how in such a large scale RoCE network, um, failures and anomaly are bound to happen, are destined to happen, right? We cannot avoid them, but the important thing is how we can monitor and diagnose system, right? So, and from the title, we already see, hey, this is
上个月
this system is built on top of Pingmesh. I think I forgot the exact year, but I think Pingmesh is published over 10 years
这
ago.
要给孩子
When
几句，
we focus on, we just started
他说这
to
做一个
understand
认
the
真睡，你说
tree and the data
特别他
center
娘，
network. And now that we are moving from traditional TCP
你
IP
别转转啊！
protocol stack to our RoCE network, and now ByteDance, I believe
要听
ByteDance
英语啊，学英语啊，你
in BUPT and Purple Mountain
你英语是个6年美国留过学，
work together to design this
6
system.
样的英语不要中了，
So
没
today
有我
we
记得记
have
得。
our presenter is Haodong Chen from a graduate student from Fudan University, and who will soon also becoming a new PhD student in Xiamen University. And after the presentation, we will have Xiang to host the discussion session, because as this reading group gradually grow, and I can finally shift some of the mediation and the discussion burden duty to Qiang. So Qiang will host the discussion, and we are honored to have invited Kefei Liu, who is the first author of this paper, and I believe a PhD who will soon get his PhD degree, right, in a month, right? Kefei, right? Okay, cool. So I think I think without further ado, we can give the floor to Haodong, and you can start your presentation. All right.
Hi everyone, I'm Haodong Chen, incoming PhD student at Xiamen University. I'm going to introduce this SIGCOMM 2024 paper, R-Pingmesh, a service-aware RoCE network monitoring and diagnostic system from Beijing University of Post and Telecommunication. First, we need to answer why monitoring and diagnostic are necessary in RoCE network. The RDMA has been used by many data center services to achieve low latency and high throughput. With the popular of large language model, distributed machine learning has become a very important uh, service in RoCE data center, but it faces a critical performance challenge, the barrier effect. The barrier effect means the overall system performance is limited by its weakest component. And the distributed training rely on many servers working in parallel, and unfortunately, it's highly sensitive to single point failure. Take the example of the fault ARNIC or a flapping switch port. Even if just one node or pod starts dropping packets, the entire training cluster will suffer from low throughput. Even without failures, the network bottleneck will hurt training performance either. One example is the ECMP imbalance. Although it's designed to balance the traffic, the ECMP may hash multiple flows to the same pace and cause network congestion on the same uplink. This congestion slows down gradient synchronization. And the RDMA-based training workloads are highly sensitive to packet drop. Unlike TCP, RNIC use a go-back-N retransmission strategy. This means a single dropped packet can force the NIC to resend a large window of packet, severely reducing the throughput. In practice, frequent RNIC issues such as RNIC flapping or temporary reset can cause timeout and degrade the service performance. Moreover, misconfiguration, especially incorrect PFC headroom settings, may lead to head offline blocking, will lead to packet timeout. As the model parameter grow and the scaling law, it rely on a larger GPU cluster for distributed training to meet the memory and the computation demands. However, a larger cluster means more device, increasing the risk and the frequency of failure and the bottlenecks. In distributed training, performance depends on the slowest node. As the cluster scale up, the fault detection and congestion control become essential to maintain training efficiency. For network team, a key question should be answered. Is it a network problem? In large-scale distributed system, many components can go wrong. The computation, storage, configuration, or hardware. But when service experience performance issue, the network is often the first to be blamed. Even if all the switches, the link, and the metric look fine, people might say, my service didn't change. It must be a network problem. Without a way to prove the network is innocent, the network team may spend hours or days tracing problem, but that doesn't exist. Not because the network is faulty, but because the network is default suspect. When troubleshooting service issues, a service log can be misleading. For example, when use the Nico library for collective communication, encountering an error code 12 bug, it typically indicates a communication timeout. At first glance, this might seem a network issue. However, it is important to recognize the network problem are not always the root cause. In this case, the error could actually be due to the GPU failure on the remote host. The targeted GPU is Zhang or Huang. It might also be caused by the misconfiguration of the Nico setup. A common mistake is the misconfiguration of the Nico GID index. If it's set to InfiniBand instead of RoCE, you will encounter the same error code 12. In addition to the network problem, service performance degradation can also be caused by non-network issues, such as degraded computation performance due to the GPU underclocking. For distributed machine learning service, which constantly repeat computation and communication cycle lasting a few seconds. And this issue often manifests as a decreased network throughput when viewed from a cost monitoring perspective. Existing RoCE network use a two-step diagnosis method. Step 1, manually inspecting configurations, logs, and metrics. Step 2, running benchmark tool, such as perf test or Nico test between RNICs to try to reproduce the failures or the performance bottleneck. While this works for small clusters, it scales poorly as the cluster grows with 10,000 RNICs. Additionally, two-step limited visibility due to the ECMP routing. Benchmark traffic often only cover a subset of paths, missing a full picture. A PingMesh is an active measurement and analyze system for monitoring end-to-end network latency across the TCP data center. It's introduced by Microsoft in 2015. It's allowed for measuring the latency between any two network interface. Since the RDMA, the ARNIC also support the TCP protocol, could we direct and deploy the PingMesh on the RoCE network to measure the end-to-end RTT with minimal development effort and effectively meet the need for the network monitoring? Extend the PingMesh to the RoCE network with several challenges to prevent interference between RoCE and the TCP traffic. A data center typically assign them to separate traffic queue on both ARNIC and the switches. The TCP probes can detect issues that are unique to RoCE, such as the congestion or RoCE congestion or packet job caused by the misconfigured PFC. By collecting 5 tuple of the dropping mesh probes and tracing their paths, the operator can further locate anomalous network device. However, PingMesh cannot tell if a dropped probe is caused by NIC or switch, which limit the accuracy using its path for troubleshooting. As shown in the figure, although PingMesh can detect an abnormal increase in RTT when performance bottleneck occur, but PingMesh use application layer measurement. It is difficult to locate bottleneck reason because because the increase can come from network congestion or CPU overload. There will be 3 key design goals of R-Pingmesh. First, accurate latency measurement using accommodate ARNICs. Since the ARNIC only expose CQE, the completion queue event timestamp, the R-Pingmesh use them to infer both network latency and end-host processing time. No need for custom firmware or modify drivers. The works out of box. Second, low overhead probing along real service paths. RoCE traffic uses UDP and XMP routing, so R-Pingmesh carefully match the probe package file to that of the service flow, ensuring the probe travel the same path. Third, accurate anomaly classification. Not all timeouts or packet job are caused by the network. R-Pingmesh first distinguish network-related issue from non-network ones, and then find whether the fault lie in the ARNIC or in the switch. Now let's take a look at the 3 key components that make up the R-Pingmesh framework. The agent runs on every RoCE host. It sends a probing packet using unreliable datagram QP, the UDQPs, which follow the same network path as the actual service traffic. This means they experience the same congestion, drops, and delay. And second, the controller acts as a central coordinator. It assigns 2 times of a ping list to each agent. The TOR merge ping list for probing all ARNIC under the same TOR switch. Inter-TOR ping list for probing ARNIC across different TOR switches, which help us monitor deeper core network links. The analyzer is the brain of the system. It performs 3 key tasks: track the service level agreement and locate the anomalies, evaluate service impacts. R-Pingmesh has 2 core functions, cluster monitoring and service tracing. The function 1 is the cluster monitor. The function is always on and run independently of service workload. Its goal is to continuously monitor the health of the entire RoCE cluster. Specifically, it monitors connectivity, packet job, and the most important, It provides a precise measurement of both network RTT and in-host processing delay. To keep overhead low, the cluster monitoring uses UD and QP probing, which doesn't consume too much unique connection resource. Function 2 is serving tracing. In contrast, serving tracing is on demand. It is triggered only when RDMA service flows are built. The agent captures 5 tuples of active RDMA connection. Then it builds a prop that match the same ECMP path used by the service traffic. This is especially useful for finding service impacting network issue as they happen. Next, look at the first function of the R-Pingmesh controller, storing unique communication information. The controller acts as a central database to store the latest global identifier and the queue pair number of all ARNICs. Because in RoCE network, ARNIC needs the remote ARNICs, GID and QPN to communicate, just like the IP address and port in TCP. But here is a challenge. The QPN are created only after the agent starts and they change if the host reboot. To solve this, each agent reports all current ARNIC QP information about GID and QPN to the controller when it's built, ensuring all the probing task has a valid and up-to-date index. I think R-Pingmesh controller build two types of pin list. First, TOR merge pin list. Each ARNIC maintain a TOR merge pin list with communication information of all ARNICs under the same TOR switches. This enable efficient detection of ARNIC level issue by probing within the same rake. The second, the monitor switch and the link level anomalies. Each ARNIC also has an inter-TOR pin list. This pin list uses ECMP-aware 5 tuples to probe across different TOR switches. R-Pingmesh use a probability formula to cover all the ECMP paths and calculate the number of required 5 tuple K to cover unparalleled cross-TOR paths with probability with 0.1990. In R-Pingmesh agent, to measure network RTT and end-host processing delay accurately, R-Pingmesh use a RoCE packet to gain 6 important time steps. Compare 3 RDMA QP type, the RC, UC, and the UD. The RC QP is the most commonly used type. However, it cannot provide the necessary time step because the sender, the security, the communication queue event is generated only after all packets are acknowledged. This makes it impossible to obtain time step 2 and time step 4, the probe sending time and the ACK sending time. The UCQP support all the required time steps, but it requires a large number of QPs. For example, under a TOR with N ARNICs, a UC requires N squared QP to fully probe each ARNIC pair. This is resource intensive and hard to scale in large scale cluster. Now let's look at the UDQP, the best fit for the R-Pingmesh use cases. All time steps are available via CQEs because of the UD unreliable feature. No need for per-peer connection. Only NQPs are needed for ARNICs. Thus, UDQP enable accurate delay measurement with minimal cost. R-Pingmesh agent use a RoCE package and 2 ACK packages to obtain all 6 time steps. Step 1, the prober send the probe package is record time step 2 when the RK finish the sending the packet. The step 2, the responder receive the probe. At this point, it record time step 3 Step 3, the responder send an ACK in reply. It's record time step 4 when the ACK is sent out. However, the probe cannot direct observe the time step 4 to retrieve it. The R-Pingmesh introduce a second ACK. When the probe receives the ACK, its record time step 5. The responder embed is processing delay, and it's the time step 4 minus time step 3 into the second ACK and send it back to the probe. This approach requires no clock synchronization and use only the CQE time step on the sender or on the receiver ARPANET. After the above process, a probe can obtain accurate network RTT, the responder and host processing delay, and the probe and host processing delay. To obtain the file table of service flow in a real time with low overhead, the R-Pingmesh uses eBPF to trace the call to the kernel function, modify QP and destroy QP function. When a service is connecting RCQP onto Onyx, modify QP is called to modify the QP attribute, including the file table. This method can easily be deployed on RDMA server without relying on special hardware or firmware. After obtaining new file tuples of service flow, the R-Pingmesh agent need to ensure that its ping list is up to date. In order to prevent probe timeout caused by the outdated information, the agent sends the destination ARNIC IP to the controller. The controller returns the communication metadata, the GID, the GQ, and the LAN. The agent combine the file table and the ARNIC information and create the ping list entries. Add this entry to the service tracing ping list. The agent will construct probe package with the same file table as the service flow. In this way, this probe can cover the exact network process used by service due to the ECMP hashing. If no active service flow, the service tracing modem paused automatically. When a probe timeout, is it really a network failure? There are three main culprits: a network fault, host failure, or probe noise. To rule out no network issue, R-Pingmesh analyzer first check if the target agent is still alive and pushing data. If it's not, the R-Pingmesh classify the timeout as a host failure. Next, compare the QPN in the timeout packet against the controller's latest QPN. A mismatch tells us the packet was dropped simply because its QPN was stale, not because of the network issue. Before R-Pingmesh hunt for switch or link fault, it must filter out faulty ARNIC to avoid false positive. R-Pingmesh leverage TOR merge probing, which send a probe between every pair of ARNIC under the same TOR switches. R-Pingmesh rule is simple. If many pairs in the same rack report failure toward ARNIC within a short window, R-Pingmesh mark this ARNIC as a faulty. Once have filtered out timeout and ARNIC fault, R-Pingmesh are left within pure network failures and localize them using a voting mechanism. This approach is grounded in binary network tomography. Links common to many fail paths are most likely to be at fault. It's fast, scalable, and pinpoint the weakest link in the chain. Let's take a quick look at the environment where R-Pingmesh has been deployed and evaluated. This deployment span both on premises and public cloud clusters, covering 10,000 RDMA NICs. It's been running stable for over 6 months. R-Pingmesh can accurately measure in a TCP checkpoint to ensure fault tolerance. All servers periodically use TCP to upload their trained model to the storage cluster in checkpoints. During this time, the RoCE network is briefly idle. The network RTT simultaneously decrease as the TCP is CPU intensive. The end host processing delay also increased. During this period, observed two instances of abnormal throughput degradation. Thanks to the analyzer's real-time analysis and its accurate ability to distinguish between RNIC and the switch level issue using TOR mesh probing, the R-Pingmesh were able to pinpoint the root cause, the package job caused by the switch port failure. In another case, the service training rate and the average throughput continues to decrease. The service team suspect that the network is congested. Then check the metric in R-Pingmesh. As shown in the figure, the RTT is also decreasing and the processor delay is stable, and proving that there is no bottleneck in network or CPU overload. It should be misconfiguration or training code bug. As shown in the table, during deployment, R-Pingmesh effective detect and locate the 14 type of problem caused by the hardware failure, misconfiguration, and network congestion, and intra-host bottleneck. Thanks for listening.
Okay, yeah, thanks, Haodong, for the presentation. Just a little bit of advice. So your slides, you remember to add a slide number to your slides. I think right now you don't have any slide number, in your bottom right corner. And the second one is really pay attention to your to the spelling. I literally spot spelling grammar or spelling errors in every single slide in your slides. Okay, you really pay attention. That's a very amateur mistake. You really pay attention to that. Would that be okay?
Oh, it's okay.
Sure. Okay, now I think after the presentation, we'll start our discussion. So Qiang, you want to take the charge?
Sure. Yeah, so let's move to the discussion part. Today we have a great honor to having the author Kefei here to share his insights and experiences about this work. So does anybody online have some questions? So just say it or just type it in the chat box. Okay, so just let me start the first question. So, Kefei, this is a great work, and I think the accuracy is pretty good. It's about 85%. So, considering the current practice, do you have any plans in the future work to further improve the accuracy of determining network-related problems? Or improve the diagnosis?
Okay, that's a very good question, and you can see it in the presentation and in my paper, and it's true that we have met a lot of problem noise, and this noise can come from just like CPU overload and a lot of host problems, yeah. Such as Linux lock and a lot of host bugs, and these bugs may lead to problem noise. Yes, this problem noise is just you found a prop timeout, but actually it's not a a network related. It's not network related, and it's just it's just a host bug. So it is really important to do some future work to split the host timeout and the network timeout more accurately. Yeah. We use Tier mesh in the R-Pingmesh and the Tier mesh just under the Tier switch and between RNX under the Tier switch, and the Tier mesh probing has some limitations. The first limitation is that the Tier mesh relies on the number of NICs under the same under Tier switch. Yeah, if there is only several a little RNX, yes, under the Tier switch, the Tier mesh is not accurate. For example, if there are only 2 RNX under the Tier switch, yeah, in this case, the Tier mesh is not accurate. Yeah, if just if just one if one RNX is filled, and you can find that the prop all the props under the Tier switch around the 50% under the Tier switch is we will experience timeout. Yeah, so we will do a lot of future work to improve the accuracy of the Tier mesh probing, or to do more work to improve the accuracy of the splitting of timeout between host timeout and network timeout. Yeah.
Okay, that makes sense. So I'm just wondering whether it is possible to combine some for example code analysis tools on the host part with the R-Pingmesh together, so they can have a better accuracy in the end-to-end scenario.
Yeah, that's a good suggestion. And yeah, we have tried to add some code in the Nico in the Nico code. Yeah, and you can add Nico log. In the Nico in the Nico code. So in the I think in the core code and in the just as communication and computation, and we can we can find whether the bug is whether the bug occurs in the communication or in the computation. Yeah, but actually I think this work is is somehow complicated. Yeah, so from the perspective of probing system, we should be simple, as we should rely on the probing system itself, and so we should rely I feel the training code and the communication code and the communication library code as so on.
Yeah, cool. So I just want to ask an interesting question. So to further automate the diagnosis and troubleshooting without any human efforts, do you think whether it is possible to rely on the large language models and some historical detection records from R-Pingmesh together, so that we can develop an LLM agent to operate on top of the R-Pingmesh, so that all of the human efforts can be eliminated?
Yeah. This is very good suggestion. Yeah, and in ByteDance, we are actually doing such such work. Yeah, we add we use the history data from the R-Pingmesh system and from the monitoring system, such as the switch logs, switch traffic, switch job log, and earning job log, and so on. And we use these logs to train ARM system, or we just use the inference of the ARM system and use this data as the input, and we use the ARM system to infer the possible. First, we can monitor and we can find the error, or we can find the network bug, network failures, and we can the second we can locate the failure, and for third we can diagnose the root cause, and we can diagnose, we use the help of ARM system, we can really reduce the human effort.
So have you already deployed this kind of system in your production practice?
Not yet. This is just our plan, and we are trying to do so. Yes.
Okay. Yeah, that's so. Let's go back to this paper. What is the most difficult part when you conduct this project? In my opinion, it is a pretty challenging and needs a lot of engineering work. So I'm just wondering, from the angle of a network researcher, so how can we get into this area and stay working on this kind of difficult projects?
From the R-Pingmesh work, the most challenging part, I think, is how to trace the service network, and this is in Pingmesh work, Pingmesh uses probing between NICs. This is a very straightforward idea, and this idea cannot really probe the service network. The service can use part of the network, not just a cluster level, and it can use this some RNICs, some NICs, some links, some switch in the cluster. So we need to do further trace the service network. So a very challenging work is whether we should to passively trace the service network or actively trace the service network. And some work such as estate, macros of estate, it traces the service the service action, such as when it calls POSEND, and when it calls POSEQE, it traces this core timestamp and to get the network state. However, in R-Pingmesh system, we use active probing to trace the service network. We use probing. We use the service QP. We trace the passes used by the service QP. We use active probing to make the props to go through the passes that are used by the service QP. And I think this idea is we spend more time to think about this idea and to discuss about this idea. And this is I think challenging work. And for the students and who want to do some researches on the diagnosing, I think we can first learn about the problems in the clusters, and we can read some experience papers and or we can discuss with the network operators, and they can feed back a lot of real problems. Yeah, I mean, yeah, in the field of diagnosing and monitoring, and we need to know about the real problems in the cluster and in the industry. Yeah, so with these real problems, so we can then discuss about or think about the better idea or better solutions to diagnose, to monitor, diagnose, and to monitor, locate, and diagnose the problems in the cluster. Yeah. Okay.
Yeah, so we need to stay close to the industrial operators and keep discussions with them so that we can find some practical and real problems. Okay, that's cool. So now we got some questions from other attendants. So in the Zoom chat box, there is a question. Among problems found by R-Pingmesh, intra-host bottleneck seems quite interesting. So the paper mentioned there are some cases where CPU is overloaded, which makes makes Yiming wonder whether there are some cases where RNIC get overloaded.
Yeah. When the CPU is overloaded, in the R-Pingmesh paper, when CPU is overloaded, it usually causes the prop timeout. And we have mentioned in the first question, and this overload is a prop noise, and this prop timeout are usually being seen as a network timeout, and this network timeout will lead to the false positive. Yeah, and the RNIC overloaded problem, it really occurs, and it occurs when the RNIC is fully overloaded, and when the in the traffic workload, in the workload of the machine learning, and in the workload of the LLM training, and when the RNA is communicating, when the RNA communicate between each other, it can consume the all of the its line rate. Okay, it can reach the line rate. Okay, and in this case, the prop you can find that the RNA props can suffer from very high RTT. Yeah. For example, in the common case, when the network is under low load, in this case, RTT is around around several microseconds, or at most tens of microseconds. Okay, and when the RNIC is under a heavy workload, and the RTT is around several hundred microseconds or even a millisecond. Yeah. So in these cases, we can use RTT to get the state of the RNIC. Yeah, to get the state of the RNIC workload. Yeah. Yeah. Another question: which type of the problem is the most common? And the most common cases found in the Binance data center is about the link flapping. Yeah, RNIC link flapping and the switch link flapping. This is the most common cases, and RNIC flapping. Are the RNIC flapping we found at the around 1 year ago, 1 year to 2 years ago, the RNIC flapping problem is very common in the Binance data center, and we discuss with our vendors, and most RNICs are from NVIDIA. Okay, or we discuss with NVIDIA and debug this problems for around half a year to 1 year, and at last we found that this problem is from the the mismatch between the RNA and the cable. Yeah, it's just such a simple problem. Yeah, but spend us around half a year to debug this problem. Yeah, and another problem for switch problem, the most common is switch link flag. Yeah, switch link flag. This is well known. Yeah, and the packet corruption. Yeah, packet corruption is also very common. The packet corruption the root cause can be the cable, the broken cable and the broken the optical model. Yeah.
Thanks for the answer. Thanks, Kefei.
Yeah, we got another question. So it is about your decision to build on the Pingmesh.
Was preferred. Okay. Yeah, we build Pingmesh. We build a Pingmesh based on Pingmesh, and we use the trace route technique to trace the passes of RDMA props. And what the reason why we design it based on the Pingmesh and based on the trace route is just because it is easy to deploy. And as far as we know, in many data centers, just such as Microsoft and Meta and Huawei and Alibaba and Tencent and ByteDance and all these companies have built their monitoring system based on Pingmesh or some systems like Pingmesh. Yeah, so we based on the Pingmesh, just the way we want to let this work easy to deploy and the other companies, the operators, yeah, they are network operators. They're after they read our papers, they can easy to they can really easy to improve their Pingmesh system to R-Pingmesh system. Yeah, and you know, such as INT and ear-spine, these systems they rely on the the advanced switch switch features. And if some old switches in the cluster and do not support ear-span or NT, this system cannot work. Yeah. So but trace route is nearly all switches support trace route. Yeah. So R-Pingmesh system can be deployed in all clusters. So this is so you use the system describes in the R-Pingmesh system R-Pingmesh paper. Yeah, you can easy to deploy R-Pingmesh system. But actually, you use this when we use this advanced features such as ear-span and T, we can get better path tracing. Get better, get a more accurate path tracing. Yeah, you know, if you use NT, you can get the port, the switch port, passed by the network flows. So, but if you use trace route, you can only get the switches. Yeah, you can only get the switches on the passes. If your clusters can support INT or some ear-span or some more advanced features, you can use INT or use ear-span to improve the path tracing techniques of R-Pingmesh system.
Yeah. Okay. Well, we got that another question from Tencent meeting. So let me just share the question. For CQE is CPU consuming usage. Considering such a CPU consuming design, pooling design.
Yeah, yes, sorry, I'm not, the network is not stable. Yeah, yeah. I'm not hear about the question. Okay, sorry.
Yeah, yeah, let me say it again. So, so in R-Pingmesh design, it uses pruning CQE. So it is a CPU consuming operation. So how does it decrease the CPU usage?
Okay. Uh, actually the polling yeah, it is. If you send a prop packet and you use CPU to pull the CQE once again, this is quite a CPU CPU intensive operation. Yeah, CPU intensive design. And actually you can use the event-based way to reduce the CPU consumption. Yeah, this is supported by the verbs, by the OFL verbs. Yes, and you can you can post in the prop, and then you can wait for the CPU event. And this operation is not CPU intensive. Yeah, and the getting the getting of the security timestamp is generated by the RNIC. Yeah, the RNIC timestamp. So the generating of RNIC timestamp is not CPU consuming. So yeah, use this event-based operation, we can actually keep the CPU consumption at a very low level. And you can see in our paper around for the host with 8 RNAs. Yeah, we have each RNA keeps the probing frequency of around 100 packets per second. Yeah, so the probing frequency in the host is around over 800. Yeah, 800 probes per second. For this frequency, the CPU consumption is lower than 3% of one core. Yeah, one core. Yeah, so the CPU consumption is at a low level. Yeah.
Yeah, I hope Kefei has answered this question. So Haodong may have another question. Yeah.
Hi, Kefei. I have a question regarding the bottleneck, the network bottleneck. I noticed that the analyzer mainly focuses on identifying failures. In practice, during large-scale cluster, if you meet the congestion, network congestion, have you used something way to figure out, such as the ECMP, the imbalanced or the incast caused by the outro, the collective communication. Have you do something apply the corresponding optimization to deal with the network bottleneck?
Yeah, that's a very good question. And yeah, actually, we found a lot of congestion problem. Yes, such as ECMP imbalance and the incast, the congestion. And for the incast congestion, as the incast is man to one, and the link between the QR to the RNA is to a certain RNA is only one has on one link. Yeah, so the man to one incast has no other way to go. So for these questions, the straightforward way is to design a better congestion control algorithm. And I think a lot of work has to do such a try. Yeah. In Binance, we use this the PCC, programmable congestion control, supported by the RNIC to design a better context control algorithm, and this context control algorithm can perform better than the DCQCN, which is supported by default by the Yangyang, and we have published the paper and in the Connect about our PCC design, and for the second, for the imbalance of the SMP, actually, many data centers has improved their load balance algorithm, and for NOR, the most popular way is to use the packet level load balance, such as the DLB, supported by Broadcom, and adaptive routing supported by the NVIDIA, and many data centers has designed their own load balance algorithm, but they are actually most of them are based on the packet level. This algorithm is very popular in most data center, and and in balance we have the similar algorithm for flow rate level or packet level load balance, and use this way we can reduce the imbalance of SMP.
Where the packet level, such as the flowlet, the route policy will add the extra overhead, such as maybe the CPU, maybe even the GPU, the extra overhead.
The overhead, I think the actual overhead is about how to deal with the reordering problem. How this out of sequence problem. You know this packet will go through different paths. So for this problem, the balance and most of the data center, most of the company will do hardware and software co-design to deal with this problem, and you can add more cache in the earning and use more software caches in the below side of the CPU, and to deal with this problem. I'm not expert about this question, and there is quite a lot of paper to discuss about this problem, and you can refer to this paper to get the answer of this question.
Thank you.
Okay. We have another question. It is a high-level question in the Zoom chat box. So, Kefei, can you please share your insights about these problems you fixed and didn't fix?
Okay. Okay. And I think for the problems, the for PMesh system and R-Pingmesh system, I think the big question is the big problem is that they are relying on agent. You know, when the PMesh is published in the 2015, I remember, and in 10 years ago, when PMesh is published, and the cluster size is not very large. It's around thousands or 10,000 of servers, and in this scale, and in this scale, in a small cluster, you use if you use agent, it is quite reasonable. And when the cluster size or the data center size goes into tens of goes into millions of servers, and in this scale, under this scale, probing based on agent is there are a lot of problems. It relies on it need to deploy agents on all of the servers in the data center, and if you have some update, you need to update the agent on all of the servers in the data center, and this is quite difficult for the millions of servers. This is quite difficult. You can think about this scenario, and so I think the training is to design agentless system. Agentless system. If you can do not rely on agent. This is quite a useful design, and in this case, you can. You do not need to deploy agent on all servers, and you can use a lot of you can use several probers and use these probers to probe all servers in the data center. And if we use this design, and these problems can be the agent problem can be solved. Yes, and we actually try to do this work, and we published a paper in the SIGCOMM in the SIGCOMM this year. Has been just accepted. So this paper will be actually presented in the September in this year.
Hope to see your new paper this September. So now I think we have we are around the ending of this meeting. So today we have a great discussion, a very widely discussion from both Tencent meeting and Zoom meeting, and I think there may be some other people on Bilibili. They may have other questions. So this work is pretty discussionable. Have many discussions. So and this is why we want to build such platform, such sharing event, so that everybody who are interested in network research can discuss some technical problems and research problems together. So this is a great chance. So now let's give the floor to Professor Xiang.
Thanks. I think the discussion is wonderful. I see lots of many questions are asked by Haodong and Richard and several other people who I don't remember names. I think very interesting. I think I like R-Pingmesh, and I also look forward to see the new paper in Portugal. So, but I think I have one more question actually. So when designing R-Pingmesh, essentially you are focusing on monitoring and diagnosis, right? So what have you guys done to prevent those anomalies happen even at the beginning? So the reason I'm asking this question is, for example, because probably some of the audience know that many of my research focus on the configuration of network layer, aka routing protocols, right? So in routing protocols, we design various verification tools to examine whether the configurations will behave as we expected if they are deployed, right? So that's what we call like we examine or we check them before we deploy them. So for example, you mentioned like PFC misconfigurations. Does ByteDance or have any tools to verify either examine or verify those configurations before they were deployed in the cluster, so that we can further decrease the chance such anomaly happens in the field? What's your take on that? Have you look into this?
This is very good question. Yes, actually, we has actually met a lot of this misconfiguration problems, and actually, the verification work I think is quite challenging. For balance, what we are done, what we are done successfully is about the data plan verification, and this is I think this is more scenario. And some papers have been published in the ActNet last year. But for the large scale for the verification of the whole data centers, this is quite a challenging work, and you know there are a lot of different RNX switches from different vendors, and they may have different they may have different versions. Versions and brands, and this switch should have different configurations. And actually, we don't know if there's a we could know that if the configuration is right. As we have a complete for each brand of switch. But we do not know whether the configuration is optimal. For example, for the ECN word mark and PS word mark, and we do not know whether this configuration is optimal. And actually, a lot of our network operators are doing a work is about the to optimize the configuration. And this configuration can change when the service workload changes. For the storage scenario, it has complete, and for the training scenario, it should have another complete. And when the cluster size grows, and this complete may change. So this is quite a difficult problem for us. And another problem is that actually there may be some bugs and maybe some oversights when the operators to operate to configure the switches on the RNX. So I think there are two problems. The first is to determine whether the configuration is optimal. The second is to find the oversight. These two questions are quite challenging in the balance data center. And we do not solve these problems well.
Okay, got you. I think I think my takeaway is that this is still an open question, because I like routing configurations, like a PFA configurations can be need to adapt to different workloads, which could be very dynamic. So it's hard to find just one single set of configuration to fit all the requirements, right? I think that's my takeaway, right? Okay, that's actually that gives me a lot to think about. I think I'm happy I'm happy about the answers, and I think there could be some new research being done. We can talk about that later.
This is a very good direction. This is a very important problem.
Cool. All right, so I think we are way past our original schedule, and it's already 12:10 in China, and also in US East Coast time. So I think we can stop here. But if any of the audience has any questions, please by all means send an email to Kefei. I'm sure Kefei will be very happy to answer them. All right, so I think this concludes our 11th meeting of our SIGCOMM Paper Reading Group, and we hope to see many of you in 2 weeks, where we will study another paper related to data center networks. All right. So for everyone, have a good day, good afternoon, and good night. Bye.